Week 11, Part 1. Greetings, everybody. I hope you are doing well, and I hope you did all right on the test. Now we're moving on to a section that sort of bridges between what we have been doing and the new stuff in optics. We'll start by reviewing the equations of electricity and magnetism and look at an amazing discovery that Maxwell did, that he derived, and we'll go through that derivation rather quickly. But I want to tell you some of that because of the history involved. There's some very interesting history going on there. And then at the end of that, we'll relate sort of all of the different parts of the spectrum of light and learn just a few very simple equations to deal with those. And then I'll go through some examples after that. So let's start just with the story of Maxwell's discovery. And we have to begin with where things were when Maxwell began his work. So these are the equations. They should sort of look familiar to you. Gauss's law, we've already studied. This is the idea that the flux of the electric field through some surface, a closed surface that's enclosing some volume, is related to the charge inside that volume divided by epsilon naught. So electric field through a surface equals the charge enclosed. You can write actually a similar law for magnetism, and this was known at this time. The time that we're talking about is a little before around the time of the Civil War, 1860s. So Gauss's law you can write for magnetism. It's the same thing, that the magnetic field through a closed surface. The only difference is it's equal to 0 because there aren't magnetic charges. There's no comparable thing on the magnetic side to charged particles on the electric side. So you have the same equation just with a 0 there. Then Ampere's law you're familiar with. This is the idea that if you walk around a loop and sort of tally up the B field as you're walking along, how much the B field points in the direction you're walking as you go around a closed path. P is a path here. Then that's equal to mu0 times any current that you encircle somehow. If you loop around and capture current, any current that's going through the area bounded by your path gets counted on this side. Ampere's law is what that was. Okay. And then last is Faraday's law, written a little differently than we have. You're perhaps remembering the rate of change of the flux on this side. This is the magnetic flux. That's why the M is there, just to distinguish it from the electric flux. We'll be dealing with both of them. But this is the B times A. So you're taking the derivative of B times A. And that was supposed to equal an EMF. Well, over here is a more elaborate description of that EMF. An EMF is sort of like a voltage, but it's kind of spread around the loop. And it really amounts to the same kind of walk around a path that you did, only you're walking along the path to see what the electric field is along the path. It's the electric field that pushes the charges and creates that EMF. Now, you don't have to understand all of this in great detail, but I want you to sort of see the broad strokes of the derivation that Maxwell carried out. The first thing Maxwell did, these equations were all known, but he looked at them and realized that there was an inconsistency in them. And so let me show you that. So he was, by the way, he was a Scottish mathematician and physicist. He was looking at a situation, say you've got some current flowing in a wire coming to a capacitor. And of course it flows on out the other side. These are, again, always thinking in terms of positive charges. Where positive charges are leaving, that leaves behind negative charges. And as they come along here, they start accumulating on the plate to build up positive charge. And as all that happens, you've got current flowing in and current flowing out of the capacitor. And now if you try to apply Ampere's law, you imagine making a ring, a circle that goes around this wire somehow, and then adding up the sort of taking the B field in the direction of the path as you walk around it, B dot dl equals mu 0 times I. And if you remember, this gets us to our usual B field around a wire. All of that works great. It gets you the B field is related to the current that's going through. This current would be puncturing through this surface that I've drawn in that bounds the path that loops around the wire. But the interesting thing is you're supposed to be able, in fact, to stretch that surface. If you imagine it as a piece of rubber or something, you're supposed to be able to distort it any which way you like. The current would still have to stab through it somewhere. But what if there's a capacitor here? You could imagine stretching it kind of like a balloon to go out and back and end up going through between the plates of the capacitor, and there would be no current puncturing through it. And so you'd get a different result depending on how your surface looked. Now, you might say, well, you should be just required to keep the surface flat or something. But even if you said that, you'd have a problem, because as you were to move your path along here, you'd say, oh, there's a nice strong B field along here. But then the minute we get to even with the capacitor, the B field disappears, and then it reappears again. And that would be true even if you're far away from the capacitor, which would make no sense at all. You'd expect these B field lines to kind of spread out and fill space and be largely uniform in a case like this, especially if you're far away from the capacitor. So this was an inconsistency. And so Maxwell looked at this and thought, well, what would it require? What must be going on in here that acts the same as current? And what he came up with is to add another term, to have it mu 0 not just times I, but something else that acts like I right between the plates of the capacitor. And he decided that what's going on in there must be an electric field. But of course, there'd be an electric field if the capacitor were charged and no current was flowing. So that can't be the whole story. While the current is flowing, what's going on is that the electric field in there is changing. And so he wrote this term to be the rate of change of psi, which is the electric flux, and as opposed to the magnetic flux that I did before. I guess I'm using two different kinds of notation here. I don't quite know why I did that. I should have made this phi sub e, would have been a more consistent way of doing it. So what he did was he decided that Ampere's law needed this extra term added to it. And then he thought these would make a perfectly consistent set of equations. So you just have to add an extra term right here. Now what I'm going to do is take those equations and look with that one change, and look at what happens in a vacuum. So what happens in a vacuum? In a vacuum, there are no charges. There's nothing there. And furthermore, in a vacuum, there would be no current. But there would be this new term that Maxwell has invented. So let's take a look at that. Here is Maxwell's equations in a vacuum, in empty space, no charges. So look at Gauss's law. It's much simpler. It's just 0 on the right. And the magnetic one is the same. Now here is Ampere's law, but there's no current. There's only this new term, which I now have written out completely. Instead of just saying the flux, I've written out what the flux would be. It's E dot dA. And down here is the magnetic flux in Faraday's law. There's a nice symmetry when you look at these equations in this case. Now that Maxwell has sort of fixed things up in one little spot, you got this beautiful symmetry between the electric and the magnetic fields. Now the constants aren't symmetric. In fact, there's a minus sign here that's not symmetric. But notice that a change in an electric field is connected to a magnetic field, and a change in a magnetic field is related to an electric field. It starts making you think that maybe you could wiggle one of these things and cause some changes, and that would make the other one change, and that would make the first one change, and this could go back and forth a little bit. Well, that's exactly what can happen. So what we're going to do in a little bit here is we're going to review how Maxwell took those equations and derived an amazing result. He didn't just fix up one equation. Maxwell discovered that those equations predict traveling waves. And that's what I'm going to do in the next video.